1. So basically we're going to look at, can a computer model developed from data using real-world observations predict motion of an object with constant velocity, meaning the net force is 0? In this lab we'll be observing an object at motion, assuming it to be at constant velocity, and then we'll be making a prediction as to the object's future position by incorporating Newton's second law, the momentum principle, and then display this prediction in a computational model. Finally, we'll compare the model prediction to the observation results on a graph. So first step is video analysis. To do this, first I selected the time frame for the video which best captured constant velocity. And this scale is, the start frame is 23, end frame 48, frame rate is 15.02 frames per second. I calibrated the object by fitting it with a calibration stick, and the diameter length was 0.067 meters. Course direction was going to the right, positive y going upwards. Object position was tracked by marking the center of the diameter of the object in motion for each frame of the video. So now I'm going to show you what that looks like in the program called Tracker. So here is the object. This is the object in motion, and here is, you can see the positive x-axis, positive x direction. So it's increasing in the positive x direction over time. And this is the calibration stick. Here are the data points. So the initial time is 0 seconds, and the initial position is 0.009 meters in the positive x direction. So for the first formula we're going to look at, we're going to need these first two data points for time and position. So observation start time is 0 seconds, total video length is 1.664 seconds, ball initial position is 0.009 meters in the positive x direction. These are the first two data points for time and position. So we're going to apply these points to the formula. Velocity equals the change in position over change in time, so that equals the final position minus initial position divided by final time minus initial time. And then we can see the velocity of the moving tennis ball is 0.5 meters per second in the positive x direction. The last observation is 1.664 seconds. Now we're going to use Newton's second law to predict the location. So the two main formulas we're going to be using is Newton's second law. So that's the final velocity equals initial velocity added to the net force, which is 0, divided by mass. Here in this case the mass of the tennis ball is 0.057 kilograms. And then we're going to multiply this by change in time. This is what the code looks like. The line of code looks like. And for predicting position, we have the final position equals initial position plus final velocity times change in time. And here's the line of code for that. So we assume net force is 0 in order for there to be constant velocity. 0 net force equals no interactions from the surroundings. So I'm going to show you the code now, and we're going to play that. So here is the code, and as you can see here, this is the ball's mass, kilograms, 0.057, and this is the ball initial position, as we already mentioned, 0.009 meters in the positive x direction, and this is the initial velocity, 0.5 meters per second. So here's time 0. This is when we chose to start our clock. This is the incrementing time is 1/100th of a second, 0.01. And so here, as long as the time is under the total length of time for the video, 1.664 seconds, it's going to iterate through this while loop, and it's going to keep reapplying Newton's second law over and over so that we get the model prediction. And we're going to see now, we're going to see what the prediction looks like, and we're also going to compare it to our real-world observations. And here, of course, we have the Newton's second law. Okay. So here we're running the program, see what it looks like, and then we're going to look at the graph. So here's what the computer model looks like. Again, it's traveling in the positive x direction over time. Okay. So questions, what if the axes were flipped? If the axes were flipped, then instead of going in the positive x direction and going in an upward slope, it would be in the negative x, increasing in the negative x direction, and it would appear as a downward slope beginning from the origin 0. So what can we know about the surrounding forces acting on the system? While we can't tell exactly how each force is acting on the system, all we know is that the sum of the pushes and pulls add up to a net force that equals 0. So we assume a net force of 0 because we want to predict an object's motion at constant velocity. So I'll show you the graph and then we'll summarize. Here's the graph. The red line is model position over time, and the blue line is the actual observed results, the position over time. As we can see here, the experiment position is underneath the model prediction, and this could be for several reasons, which we'll go over. So the forces in the surround are the Earth's gravitational downward pull. The friction and air resistance could cause the net force to not equal 0. The ball might not have been rolled in a straight path. The lens could have distorted the object's frame. The ground might not have been even because there were dips between the floor tiles, and possible shooting of different frames per second due to low light conditions could have all affected this. So this means that the model is good for predicting objects in motion at constant velocity. However, this object did not have a net force of 0, and this is why the model turned out to be an over-prediction.